Good afternoon, everyone. We'll resume the session now with graph theory. So I'll start with the basics of graphs. So I think we all know what a graph is. Anyway, I've given the introduction here just to have a quick look. So graph, as we know, is an ordered pair consisting of a vertex set that is basically a non-empty set whose elements we call vertices, and an edge set, which is a set, possibly empty set of unordered pairs of elements of the vertex set, right? Unordered pairs of vertices. So we think of this as whichever two elements are there in an edge, those are the endpoints of that edge, right? When we draw the graph. So for example, here, there's a graph shown here. As you can see, the vertices are labeled A, B, C, D, and the edges are AB, AC, AD, BC, and CD. Okay, so that's given here just for reference. So the definition that I'm using insists that the vertex set be non-empty, whereas the edge set may or may not be. But there is another alternative definition which some authors use, some textbooks use, where the vertex set is also allowed to be empty. Okay, so I'm not using the definition. However, Sage Math does. So in Sage Math, you can have a graph without any vertices also. Okay, I will not generally be considering these graphs, but it is there in Sage Math. So I just want to tell you that. Okay. So here's an example. As I said, this is the vertex set and this is the edge set. So this is the formal definition of the graph. Of course, we find it easier to visualize the graph, right, by drawing it in some manner. And so the visual representation is also given here, and I'm sure you can understand it. If not, please ask me. If anyone is completely new to graph theory, please let me know. Okay, so now how do we define graphs in Sage? There are several ways to do this. Okay, so we'll start with one of the basic ways, which is as close as possible to the theoretical or formal definition. Okay. So consider graph G with vertex set V and E. Suppose the vertices are V1, V2, etc. Vn. Okay, and the edges are E1, E2, etc. But in Sage, if you want to define a graph by specifying its vertex set and its edges, the simplest way to directly do this is to use this command. G is just to name the graph. So you already know from the previous session about how to assign values to variables and so on. So you can see that here we are creating a variable called G and assigning some value to it. That value is defined by this function, this graph function. Actually, the graph is we have not studied that class, but if for those who know some Python, this is actually the constructor of a class called graph. So we are creating a graph object, or we are instantiating a graph object. Anyway, if you don't know that, no problem. Just think of it as a function that creates a graph, one function that constructs a graph. So what is the syntax of this function? The name is graph with capital G. That's very important. Python is case sensitive. So even in the previous session in the chat, there were many queries. Here also there were many queries where I saw that you are getting errors because you have not used the correct case. In some cases, you have used, in some instances, you've named a variable with, let's say, small w, and then later used capital W and trying to call it. So you have to be careful about what case you're, whether using capital letters or small letters. Okay. And especially for the standard or the library functions of Python, the library classes and functions of Python, you have to use the correct case. Otherwise, you will not, right? So here it is, capital G graph bracket. Now this is, again, I'll temporarily zoom in to show you. This is the curly braces, flower bracket, open flower bracket, then first vertex, whatever name you want, you can give it. Okay, so I'm just going to call it V1. Actually, I'll show you in the particular example. So in the general case, suppose you have a vertex labeled v1, v1 colon, then a list of neighbors of v1. So this will be a square bracket with a list of other vertices which are adjacent to v1. Then comma, v2 colon, list of neighbors of v2, and so on. Okay, that is the syntax. And then close flower bracket, close simple bracket. So in particular, in this example, in this above example, how to define this graph. It will be easier if you look at the example rather than the general case. Okay. So to define this particular graph, how do we write it? G is equal to graph of, I want to label the vertices A, B, C, D. So I'll give A colon, A is adjacent to which vertices? B, C, and D. So A colon, B, C, D. Actually, I'll type it here so you can see it being written, right? So A colon. Now the neighbors of A, what are they? B, C, and D, right? Comma, close bracket, comma. Next vertex is B or whatever. Okay, I'll give B. It's adjacent to C. Okay, so can you point out some possible problem here in what I've done so far? B is adjacent to A also, but I'm using the graph function. There is a separate digraph function for directed graphs. So those who know the definition of directed graph, where edges can be directed, there is a separate function or class called digraph. If I'm using that and I want A and B to be adjacent to each other, then I have to specify A as a neighbor of B and B as a neighbor of A. But here, I've already said that B is a neighbor of A. So it understands that A is also a neighbor of B. I don't have to specify that separately because we are using the graph class or function, which is only for undirected graphs. So that redundancy doesn't have to be given, right? The redundant information does not have to be given when you are defining the graph. That's one slight advantage. Okay. Again, I'm not separately specifying that D is a vertex because it's already known, right? I've already given it in one of the list of adjacencies, right? So that doesn't have to be separately specified that D is another vertex, right? So if you do this and evaluate it, now the graph is defined, but it is not displayed. So again, from the previous session, you know, just defining an object does not automatically display it. You have to give something else like print or just the name and evaluate something like that, right? So here for G, for a graph, we will do G dot show. Show of G is also fine, right? So you can also do, okay. I will tell you why I use G dot show, because if you use G dot show, there are some optional arguments that can be given to customize the display. Okay, so right now I'll just do the default one. You can see that this is displayed in a better manner, the earlier one, where I have not shown the commands I used. But here the display is a bit not so nice, right? That's because the earlier one I have customized. Okay, so I'll show the customizations also. This is G dot show. Each time you evaluate, it's going to possibly change what is displayed because the layout is determined randomly. Okay, the layout is determined by an algorithm in some random manner with some principles are there, but in some random manner. Okay, so each time you evaluate the cell, it will possibly change the display. So try this. What we have done so far, please try. Any questions? Online participants. Sorry. Yes, the graph, is it? The picture, right? So there are many ways to, at least 2, 3 ways to do this. One is you can directly, because this is basically a web page, which is on your computer. Web server is your computer, but it is a web page. So you can just right click and save. That is one option, not the best option. If you just quickly want to save that image as a PNG file, you can do this, save image. You can also export it as a PDF image, which is scalable. So if you want to embed it in, for example, a LaTeX file, and you want to embed it as a graph in your, as a figure in your LaTeX file, then it is better to use EPS or PDF, which is scalable, not the PNG file. Okay. So then you can also save. So actually this I'll, yeah, so there is something in the chat. Okay, the question is directly to me. Text and code. So that we will discuss later. Um, okay. Right. So another option is save. Okay. So save, let's see, g.save with file name. So if you give, say, something like graph1.pdf and evaluate it, here you will not see any output, but now it is saved in your home folder. So if you go to your home folder, oh, right. So sorry, this is not. Actually, that will save the graph object. That's a different thing. Let me. Yes. Yeah. So g.plot, g.save is for saving the object, the graph object that is generated. Uh, that is, so I'll explain that. So if you directly give g.save, right? So this graph, this g that we have defined now is one of the objects in Sage, because as I said, graph is a class, and this is an object of their class, which means it has the complete definition of the graph in it. It's not the picture. This is the picture. But this G, the variable G, is the information, all the information about the graph is in, what are the vertices, edges, and so on, right? So that object you can save. Why would you want to do this? Suppose not the small graph, but you have done carried out some big computation. And after some hours of computation, you have generated a graph, right? Which is computed from a lot of data. Then each time you close this and open it, again, you have to do this computation. That is not efficient. So you can save the graph object there, graph object or whatever object is there. In MATLAB, if you used, you may see that you can save matrices, right? You can right click on there is a list of variable list. You can right click and save it there. You don't need to copy paste anything. You just save it, then open it. Similarly, in Sage, whatever object you create, you can save it directly and then load it from the saved file instead of computing it again. Sometimes we compute things which will take hours to compute, or even if it's a few minutes, it's inconvenient because so many objects may be there. So we can save all of them and then load them from the saved file. That is why the dot save is there. But maybe we'll discuss this later in the more advanced parts, right? Once we compute such complicated objects. So right now, to save the picture, right, the figure, what you can do is g.plot, open bracket, close bracket, because it's a function, dot save, and then give the file name. So with the file name, whatever extension you give among the familiar, well-known extensions like PNG, possibly JPG, PDF, EPS, it will save it as the correct object. Okay. If you give some unknown or very obscure extension, it may not work. But PDF, EPS, GIF, JPG, these will work. Okay. So I recommend that you save it as PDF or EPS because that is scalable. So as you can see, this is the PDF. Even if you scale it, it does not get blurred, right? Whereas if I save it as a PNG and then I scale it, it will get blurred. So this is a general advice. Any other questions? In your Sage home folder. So I don't know if you followed my installation instructions, and I have shown you while installing itself, it gives you an option to set your home folder. Okay, so let's go back to the home screen. I'll show you. Yeah, you can also give a custom path and save it. Yes, that is also an option. But then you need to know how to give string, how to define strings in Sage, because slash out has to be given as double backslash as an escape character. Correct? Huh. No, here if you want to give the path. Suppose I want to say C slash, but you need to use escape characters, right? So yeah, that uh, can be done. So let me show you anyway. See, when you open Sage or Jupyter Notebook, basically, the first page that you see, that is your Sage home folder. Okay, so this is the fold. This is actually a folder on your computer where all the files that you create, all the notebooks that you create are stored by default. So in my case, it is this folder. So whatever is there in this folder, that is being shown here. Okay, this is, as you can see, I have set this as my path for Sage Home. In the installation instructions, I have told you to select a reasonable folder, reasonably accessible folder, like either in My Documents, you create a folder for this called Sage Home or whatever. Or if you have some research work folder like I do, then in that, right, wherever. So that later also, if you are changing your laptop, changing your computer, or if you want to backup, you can easily get it from there. Because the default location is somewhere inside some user folder. You may not be able to find it. So this is where it is saved. But as he said, you can also give a particular custom path and save it there. But again, there are some nuances to how to give strings in Sage. So again, we'll see that later. Any other questions? Okay. Yes. So as you know, so if you give LaTeX of G, that will take some time. Yeah, it will give you the PGF code, I think. PGF ticks, yeah. So many of the computations, when you're doing that computation for the first time meaning after opening the notebook, when you're doing it the first time, it may take some time because it needs to be it needs to load some package from somewhere. Yeah, I think that's from earlier. So from earlier, yeah. Because already it was in a direct chat because that time some technical issues there. Continue. Yeah. Thankfully, I get notification when it's direct message, so I can see. Yeah, okay. Right, right, yes. Sorry, so I can directly answer. The earlier answering in chat. So there is one question from an online participant. What is the difference between drawing a graph using LaTeX and using Sage? So when you draw a graph in, say, Tix, for example, or by using any other tool for drawing graphs, obviously you have to draw the entire graph by yourself, right? Whereas if you're using Sage, then in this case, we have merely defined the graph in an abstract manner. We have not said place this vertex here, place that as vertex there, join them by a line, and so on. We have not given any such specific commands. We have just given the theoretical or abstract definition of the graph. Plotting of the graph has been done by Sage, and then it is giving the LaTeX code when we ask for it. Okay, as text picture, okay, which you can copy paste and use. Right. So the advantage here is all this code you don't have to write. You just have to write this much, right? The definition of the graph and then LaTeX of G. Other thing is, very often you don't even have to do this because in actual research, when you're drawing graphs, you will not be drawing the graph manually. You will be obtaining the graph from some computation. So you may say that I have these smaller graphs, and then now take the Cartesian product of this, and then corona product with that, and then union with that, right? And then take the complement. This computation I do. I don't then manually compute what is this graph. Sage will do it for me, right? So all that big computation is done, generating a big graph. Now, if you ask for the LaTeX code of that, it will give you automatically, right? So you don't have to sit and draw the graph. That is the difference. Okay. Yeah, so we'll see graph operations and so on. Again, you have graphs defined from matrices, graphs defined on algebraic structures like groups and rings. So all of this, you will be computing the graph using Sage rather than manually computing it. So in that case, there's a huge difference between the effort of typing in this command versus drawing it by yourself. So here we have given the vertex labels, right? Colors, there is some amount of customization that you can do, but in the yeah. So that is where this show or plot commands. Yeah. No, that yeah, it will always show. So the default thing is it will show the vertex label inside the circle, right? But I think there is a network X package which shows it differently. Is it network X only, right? Yeah. So one thing, yes. No, they're asking normally we draw the graph, like plot the graph as a dot, vertex as a dot, and then write the label above. So that option is not there here. Yes. Yes, we can, because we here actually I've given a string. So suppose I gave A1, right? No, not here. I should give dollar. Yes. So this was just a string. Okay. So actually, wait, let me go back to what I had earlier and discuss this in a little more detail. So as you can see, I've given these quotes here, right? Single quotes. Why that is given is because what would happen if I just gave A without the quotes? Can you guess? If I gave A, B, C, D, etc. without quotes, what would happen? Yes. It is some random value or it is undefined. If you have already assigned A equal to 1, B equal to 2, etc., then it will take those values. If not, if you're not already defined A, B, C, D as variables, then they're undefined, because if you give A without quotes, in Sage, what is it? It's a variable. It's the name of a variable, right? If you're not defined it, then it's an undefined variable. So it will just give an error. Yeah, as you can see, if I evaluate this, it says A is not defined. Right. As you said, if I suppose I first say A is equal to 1. Now if I, yes, now it is giving 1 because I have defined A as 1. So A is not the string A anymore. It is a value 1, right? Its value is 1, right? So if you want strings as labels, I mean, if you want some letters or something as labels, then you have to give it a strings. And to define a string in Sage or in Python in general, we use single quotes or double quotes. Both are interchangeable, right? You can use double quotes also. There's absolutely no difference. Okay, as per your convenience. So I'll just use single quotes. So each label here is a string. I can give longer strings also. So can also do this. There is no problem. No. So now this is just a Python string. Okay. So as you saw earlier, if I give A underscore 1, it is going to very faithfully print A underscore 1. But if I want LaTeX, so which you can do in Sage, not Python in general, right? In Sage, Sage also has LaTeX support by default. So if you do give something in dollars, it will understand that it's supposed to be LaTeX. Yeah. No, because it's a string. If you give it in dollar, then so let's see what happens. So you see that here, there is a difference in the font, right? That is the same. When you use LaTeX also, if you want to write in math, A is equal to 1 or just A also, you should give it in dollar. Because if you give without dollar, it will give A with the different font, which is a normal text font, not the math font. So that's not the correct way to do it, right? So here similarly, the display will be different, but there is no error because, oh, you mean when I want to refer, yeah, I'll come to that. So yes, yes. Yes. Yes, 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 correct, correct. Dollar, yes. So if I give dollar B, even without this one, okay. So now you see what is the problem? That's a good point. So what is the problem here? Not just the font. Now the graph itself is different. Why? Because one vertex is dollar B dollar, other vertex is just B. Right. So it thinks it's two different vertices. Right. That is the thing. So then, as you said, you have to consistently follow that. So the easy way to do this, if you want LaTeX vertex labels, but also the convenience of not typing big commands every time, what you should do is simply define variables. A is equal to string, right? String $A. B is equal to string $B. Yeah, unless you like, suppose your main purpose is to get the, yeah, correct. But suppose your main purpose is to generate the graph to get the TIX code. Then of course it is better to do this. Then yes, use the variable names, right? Don't use the strings anymore. So you should be able to understand what is going on here. I have named the strings with variable names, right? Now you can see that there is a difference in the display. So here you can even give any math command. So I can even give oh yeah. So I forgot my own thing about escape characters. Oops. Huh? Oh, right. Okay. This is stricter than usual LaTeX. Spaces is not counting. Yes. Actually, just normally when you write in LaTeX, you can just give frac space A4. Right. Here, for some reason, it's not. Okay. So now, actually, we'll come back to this because I don't want to spend more time on plotting the graph. We'll look at actual things you can do with graphs. Okay. So shall we move on to the next thing? Yes. So let's see some more examples of this. So you don't have to use string labels. You can just use 0, 1, 2, 3, etc. Okay, so I'll say 1 is adjacent to 2, 3, 4, 5. 3 is adjacent to 4, 5. Let's say 4 is adjacent to 5. Oh, right. Forgot the law brackets. Yes. So yeah, customization of the vertex colors, etc. Yeah, it can be done, but maybe if there is time, we'll take it up later. Okay. There are options. Actually, you can also explore. So there are options to customize colors and so on, especially in the saving, when saving the graph also, there are possible customizations. Another thing is, since you have the TIX code here, you can also easily modify that. Okay, yeah, if in Sage display itself, in the notebook itself, if you want to modify the display, there are options. But if your only aim is to like embed it in some document, and there you want to customize, you can just take the TIX code and customize. It's also not too difficult. Sometimes that's the easier option, depending on how much customization you want. Okay. Yeah. So another thing is, how can we rectify the error when showing the graph? I'm not sure what the question is. If you have made a mistake, you have to go back to the cell where you defined it, right? And then, so suppose I made an error here, like I did earlier. Possibly, yeah, that is a problem. So here the problem is because it's a string in Python, backslash is what is called an escape character. Right? So backslash followed by certain particular letters have some special meaning. So if I actually want backslash itself instead of some other character, then I have to give double backslash. That's the thing. So that was the error. So if I forgot that and then I try to show the graph, it will give me an error. So to correct the error, if I understood your question correctly, here if you evaluate it again, it's not going to get corrected automatically. So you go back to that cell where the error was, correct it, evaluate it again, shift enter. Okay, press shift enter, evaluate it again. Then come back to the cell, evaluate it again. Okay. So, yes. R, okay, okay, like F string, okay. Okay, again later. Okay. So you want to identify the mistake from the error. Is it? That's what you mean. Okay. That takes some practice. So the basic thing is you should check the last line. Okay. Yeah, I think what your interpretation is correct. So, um, so, so the anatomy of the error message is like in the last line, you will see the actual error most probably. Okay. Then it traces back through this to find the last instance of where the error is. So very often that will not be something you can understand because it is somewhere in the source code, which is not here, which is not something what we wrote, right? Not something that we wrote, but rather this command being used by, or is it's calling some other function somewhere already defined in the library. So in that library function, here this line has resulted in an error. And where did that error come from? That error came from this particular line, right, where that was called. Okay. And in turn, that came from here and so on. So if you scroll down through this, it is going backwards in the latest instance of that error to the root of the error. So the root of the error is almost always found in the last few lines. So here, if you see this, it says value error. So value error means somewhere where it expected this kind of value, some other kind of value was found, right? That is value error, basically. Okay. And it's also mentioned here, expected end of text, found dollar. So sometimes it's not easy to understand what it is, but at least from this, you can see that something is going on with this because this F from the fraction command is missing, right? So again, you have to know some basics of Python. So then at least then you'll remember that, okay, this is not just LaTeX. I'm writing in Python. So this escape character is required. Okay. Yeah, some of the errors may be easier to decode. Like when you're doing linear algebra, for example, you may get some dimension error or something. Then you know, okay, maybe I'm trying to multiply matrices which are not really compatible for multiplication. So scroll to the error message and then see, okay, it does definitely take some practice. Okay, so we have now defined another graph H. Yes. So one thing is, what are the different ways of customizing the display? One is there is a layout command which I can use. So layout equal to, as a string, there are a few options. One is the circular option. Specific to graphs. Yes, layout is specific to graphs. So g dot show of, so if you use show of g, then you can't use this. This one doesn't have it. G dot show has because it's specific to graphs. So this goes with circular layout. You can't see a circle because just 4 vertices. If I had 10 vertices, it will look closer to a circle. But the point is, the vertices are actually plotted on a circle. So the layout is better. Okay. So you can see this is closer to the earlier one, which I've displayed here without showing the code, but it's still not quite the same because size is different. So there is another option where you can change the figure size, which is called fig size. Fig size equal to, let's say 3. You can make it larger or smaller according to your wish. Then here I've disabled the vertex labels. Vertex labels equal to false. Similarly, edge labels equal to true. By default, it's false because it's not a labeled graph, right? But if you have labeled graph, you can give edge labels equal to false or edge labels equal to true. There are many other options. You can explore the documentation and find out. Several customizations are there. Okay. Again, everywhere case matters. Then vertex underscore labels. Okay. Hmm? Yeah, vertex colors also. Yes. But then again, you have to know how to define colors. Yeah, basic colors are there. So, okay. Vertex color, right? Okay. But you have to give list of colors, right? If you want it, any tool you use, right, okay. Yeah, okay. So if you give a list of colors. So you can't give some very obscure color, like mauve or something, but basic colors are there. I think the basic HTML colors. The further customization is possible using RGB and so on. Yeah, again, I don't want to spend more time on the display part, but to quickly tell you about the layout, because that's very useful. Circular layout is one. The default layout is something called Spring, which is basically an algorithm that automatically calculates a reasonably good layout. Okay, Spring layout is the default one. You don't have to specify it actually. That is the default. The other one is circular. Then there is a tree layout, but you can only use it for trees. So here it will give an error because it's not a tree. This graph is not a tree. Okay. Tree layout is there. We'll see it when we discuss trees. Okay. So now going back to this. Here we have two graphs. Okay. G and H we have defined. So now let's look at some basic parameters associated with graphs. The very basic parameters, not the advanced ones. So just order, size, degree sequence, and so on. So the order of a graph is the number of vertices in the graph. Size of the graph is the number of edges. Degree is for vertex, not for the graph. Degree of a vertex is number of edges incident with it. Or in the case of simple graph, because we are discussing simple graphs, it is the same as number of vertices adjacent to the vertex. Okay, same thing. So in maths, we write this as degree G of V or simply degree of V, right? And we also know the degree sum formula, also called the handshaking lemma, which says that the sum of all the vertex degrees is equal to twice the number of edges of the graph, twice the size of the graph. Okay. So let's verify this for the graph defined earlier. So how do we get the order, size, and so on? So G dot order, that will show you the order of G. Okay. Similarly, G dot size will give you the size. You should actually you should really guess these things. That way you'll remember better also. If you guess it and get it correct, you'll remember. If you guess it and get it wrong, then also you'll remember that you got it wrong. So how to get, okay, so far. Now, what about, oh yes. So now what about the degree of a particular vertex of G? Again, yes. Yeah. How do you think we can get the degree? Is it G dot degree? Degree of the vertex, right? So G dot degree, yes, because degree is a function defined for a graph of the vertex. So here, remember, we have defined vertex as these strings. So conveniently, we have labeled them as, I mean, we have assigned variable names to them so that we can use those variables. Otherwise, you have to give the exact string, right? So G dot degree of A without quotes because we define the variable. Huh? That is degree sequence. Simply if you give 0 degree, but I think increasing order. Decreasing order. That is the correct degree sequence. No. Order of the vertices. Okay, yeah. Which we don't. I mean, which is also fine. But I'll come to degree sequence. So just define here. Oh, I did not complete writing this. So now let's verify the handshaking lemma or degree sum formula. So let's do it the hard way first, which is G dot degree of A plus G dot degree of B plus G dot degree of C. So we'll automate this soon. Okay, this is the first LHS, let's say. What should be the RHS? Twice the size. Yes, that's true. Best way. Right. So I'm giving double equal to, you've seen again, you've seen if statement, if then statement in the previous, right? So this double equal to is for checking equality, right? LHS is equal to RHS if you give it's true or false value. We are not saying that, we are not saying assign RHS to the value of LHS. We are asking is LHS equal to RHS, true or false? So you can just print the LHS and RHS and then see whether they are equal, right? So you can also do that. Yes, both are equal to 10. Because the degrees are 2, 3, 2, 3. Correct. Yes. This zoom fine or you want further? This zoom level, this one is fine or more? Is visible? Yes. Yeah, that one was a little too big. Yeah, if you want at any point something is not clear, I'll zoom in further if you just tell me. Okay, so the degree sequence of a graph, as you know, is the take the list of all degrees of the graph and arrange them in non-increasing order, right? Largest degree first to smallest degree last. So that can be obtained by doing G dot degree sequence. So yeah, again, use tab completion. You can usually guess, right? You can usually guess this and see what all are there, right? There are lots of commands related to degrees themselves, right? So degree histogram, degree iterator. So degree sequence, just see what it gives. Yes, this is the sequence of degrees in non-increasing order. Yeah, the other one will give in the list of order of vertices which you define. Yes. Yeah, so as he said, G dot degree is also there, but it's not the same order. Right. Is it? It happens to be same. Why is it? No, no. B is at. Yeah, yeah, okay. No, 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 correct. Yeah, C is of degree 2, no? Yeah, so it is, this is also the same thing for some reason. Possibly they have defined it as an alias of this function. Don't know. Yeah, similarly, okay, this is for H. Huh? Vertex order, but why is it? Oh, yeah, yeah, it is vertex order, correct. Yeah, okay. Why? A is adjacent to 3. Right. A, B, C. No. So B is the second vertex, no? So why didn't it give 3, 2, 3, 2? Should have given 3, 2, 3, 2. Okay, I'll decode that later. I'm not sure why. Anyhow, degree sequence will always give the correct degree sequence. Okay. Now, instead of doing this, G dot degree of A plus G dot degree of B and so on, here especially because it's a slightly larger degree sequence, like 5 vertices there, and it's a bit tedious to write all of that. So what else can you do? Take the degree sequence and apply the sum function. Not sum function, sum function, SUM, sum. The sum is there in Python itself, no, it's not specific to Sage Math. It gives you the sum of the elements of any list of numbers. Okay, how can you get the some other parameters related to degrees, which is minimum degree, maximum degree? How will you get that? Yes, sir. We can label edges also, but edge labels are for display purpose. Yeah, but yes, so edges also, I'll discuss how to now add and delete edges and so on. So there we'll see how we refer to specific edges. Yes. So how will we get the minimum and maximum degrees? Yes. Min now. So there is again Python command is there, which will give you the minimum element of a list. right? And similarly, the maximum element of a list, which are min and max. So again, instead of sum, in fact, oh yeah, again, I keep forgetting the escape, yeah, double batch. Okay, then now I will show the R command. R, R or F? R on. No, F string is there, but F string does something else, not this. Wait, 9.3 has. Huh? Oh, yes, yes, yes. Correct, correct. Yeah, yeah, correct. Oh, yes. And print is not going to do this. So print is Python print command. So it's not going to do that correctly. Show is also not going to work for multi-argument function. Is it? Yeah, it does not. So I'll give in and just. Okay, I'll compromise. Yeah. Okay, minimum and maximum degrees, right? Then what else related to degrees? What is a regular graph? Graph in which all the vertices are the same degree. So G dot is regular, false. This is not a regular graph. H is also not a regular graph. Okay. These are not regular graphs. So we will define regular graphs very soon. Then we will see. Okay. So for example, suppose instead of just the vertex degrees, I want to actually see the list of vertices of G, list of edges of G, although I defined it in this case. In general, maybe you get the graph from somewhere else. You want to actually see the list of vertices. So the command is, the function is G dot vertices. Similarly, G dot edges. And you'll also understand how edges are specified because we did not give any labels to the edges, as I said. It will be clearer if you use it for H because for G we have given some very complicated vertex labels. That is the edge label. Edge label meaning not the name of the edge, but rather the label that you are putting on the edge. Like if you want to label the edges with something meaningful, like some distance or something that you're representing. Right? Not actual graph parameter, but something. You can give any string as a label. Like you can label some vertex saying friend and some label saying enemy and so whatever. Some signs. If you're dealing with sign graphs, you can give signs as labels, so on. So as you can see, the edges are actually, in this case, they are given as ordered triples consisting of two vertices, which are the end vertices of the edge. And then, as I said, the vertex label, right? But if you want to refer to the edge of the graph, you can just give the end vertices. You give it as an ordered pair like 1, 2, but it is treated as an unordered pair. Even if you give it as 2, 1, it is the same edge. Again, because we know that it's an undirected loop. So suppose I say, so again, let's look at G here. Okay. So now, actually, this I'm calling it A and this is C, right? Suppose I want to delete the edge AC. So there's a delete edge command function. Huh? No, I want to delete AC because I now want a regular graph. So I will do. What did you say? PCs? Because you want to do the other label. No. I have already labeled. Remember, I have the variable name, so I'm going to use a variable name. I'll do G dot delete edge AC. Okay, let me evaluate this. So why did it not change? Because I did not show the graph again, right? Just evaluating it will not change the previous outputs. Okay, so you have to show again. You can evaluate this cell again. Sorry, you can evaluate this cell again, or you can write here. Right. So now it is changed. Now, if you ask it whether G is regular, it should say yes. Yes, now it is regular. Now all the vertices have degree 2. Okay. Now what else do you have with graphs? Some graph operations, for example. Basically, with one graph, what operation can you do? What is the most natural operation you can do? Other than deleting vertices. So, okay, you can add and delete vertices and edges. How do you add a vertex? Add vertex. Most Your most obvious guess is probably correct. Okay, once you get the basic structure of how these functions are named, your first guess is probably going to be correct. So if you do G dot add vertex, let's say, or maybe I'll add to H because it has numbers as vertices, right? So I'll probably go for H now. Let's say I add a vertex 6. By the way, when you are trying it on your computer, you don't have to give this fixed size equal to 3 every time because I have zoomed in so much, I have to reduce the size and you can just do H dot show. Yeah, so it has added a vertex, but it is not adjacent to anything because we did not add any edge. So I can add edges also. If you're adding an edge, you don't have to add the vertex in advance. Again, it is smart enough to understand that when you add, suppose I add an edge labeled 6, 7. 6 is already there, but 7 is not. Right. So what is it going to do? It will add the vertex. This is in a way good thing because it's easy for you. You don't have to add the vertices first. But in a way, it's a bad thing because by mistake, you may add some edge which you did not intend. If you're not careful, if you're doing it in an automatic manner by using a loop or something, where you have an iterator, some index I and some index j, and then iterating through those, you're adding edges. If you don't write it correctly, it's very easy to add edges which are not really supposed to be there. It will not tell you that these vertices are not there. You just add the edges. And if it's a big graph, you may not be able to see and verify whether it's correct or not. So you have to be careful with that. That is the thing. Right. Or afterwards, you verify whether the order has remained the same after adding the edges. Right. Okay. So now what if I want to add many edges? So then there is add vertices and add edges. Both are there. So again, suppose I want to add edges. Now see, 6 and 7 are not adjacent to anything. So I'll make, let's say, 5 adjacent to 6. So now for whatever many things I want to do. Basic Python thing is list. Right. List is defined in square brackets. So I'll just show you a list first, which I've already seen many times. So this, for example, is a Python list, right? Square bracket, elements separated by commas. That's a list. So to add edges, what list do I have to give? Here I have to give a list. So first of all, I'll open and close square brackets. Here, what do I have to type? That's the question. I want to add an edge between 5 and 6. So what to do? Ordered pair, 5, 6. Although I'm saying ordered pair, it will be interpreted as an unordered pair. For Python, it is an ordered pair. For the graph, it is an unordered pair. Okay. So remember, these square brackets are what makes it, or what make it a list of edges. Okay. Don't forget the square brackets. Okay. 5, 6. Then let's say 2, 7 also. So 2, 7. Then let's say 4, 7 as well. I can even give 7 for it. Hardly matters. It doesn't matter at all. Yes. Yeah. So it has given this graph. Similarly, delete edges, delete vertices. Multiple edges can be deleted at once. Same format, list of edges. These spaces are optional. I'm giving it for the sake of readability. Sometimes the circular layout is not the best. Okay. Structure is actually less obvious when you give this. Right. Yeah. Basic default layout is often the better one. Okay. Yeah, for economy of space, you can give circular layout. But sometimes to see the structure more in a more intuitive manner, use the default. Okay, so yeah. Now, other than this, just with one graph, what operation can you do? Complement. G dot complement. So let's say I'll label it as gcom. Okay. You can give whatever labels you want. Yeah, I'll just give maybe gc. Gc is fine. You can directly give g dot complement dot show, but I'll store it so that you can see this. So remember now our modified G is C4, the cycle on four vertices. Its complement is 2K2, two edges. It's joint union of two edges. Right? So I can also, if I just want to see the graph, I can also just ask for it to be shown without first defining it. Hmm? Is it? Yeah, if you want to see them side by side, by yes. But is it self-complementary? Huh? Looks like it. 4, 3. No, it's the same, I think. Pure order degree is 3. Okay. Oh, yeah. Okay. So, anyway, since it came up, we want to know whether these two graphs are the same. So, if you are not able to notice it easily, like Shashwat, I was really struggling to see whether they are the same or not. So, how do you check? How do you check whether these are the same graphs? Graph isomorphism is what you need. You can't check label by label, right? It's this vertex 1 here is part of the C4. Here, vertex 1 is part of this C3, right? It's also part of C4. It's also part of C5. So even that is not easy to check. But anyway, even if you verify label by label, that is not really telling you whether the graph has the same structure or not. Graphs have the same structure. You want to check whether the graphs are isomorphic. So what is the formal definition of isomorphism of graphs? It's a bijective or one-to-one onto mapping from the vertex set of first graph to vertex set of second graph, which preserves and reflects all adjacencies or preserves adjacencies as well as non-adjacencies, right? Edges and non-edges, meaning whenever, so F is a bijection from a vertex set of G to vertex set of H, such that if U and V are two adjacent vertices of G, then F of U and F of V are adjacent vertices of H. And if U and V are non-adjacent vertices of G, then F of U and F of V are non-adjacent vertices of H also. In other words, U and V are adjacent G. If and only if F of U and F of V are adjacent in H. Okay. So again, hope you know that basic theory of graphs. So to check that, guess, yes, is isomorphic H? No, not. Right. Yeah. G equal to H. Okay. So G equal to G is true. G equal to H is false. But misleading here because they are not isomorphic, but they are also not equal. So let's see. We know this is G, right? I can easily define a cycle, but I don't want to give that away now. So I will manually define it. So G and H, G and K are the same, right? G and K are same, correct? Yeah. False. Why? See this, not just labeling. Even if I give the same labels, it's going to say false. Because this equal to, you have to differentiate between code and maths. So equal to is something in Python. It will tell you whether two variables are the same or not. Meaning two variables are the same object or not. Okay. Yeah, it can also check the values. It can also check values in the case of simple objects like numbers, numerical values or strings. It can check the equality of integers or real numbers and strings and such simple objects. But graphs or vector spaces even, right? Or these are more, even matrices it can check because it is built. Actually, it depends on whether it's defined or not. Okay. So if you have your own custom object, which you're defining using a class, then it is possible to define the equality operator, the double equal to operator for that class to make it do whatever you want. So in this case, it is not defined. So it is checking whether these are the same object in Python or not, which is not at all the same as what we want. Right? It's nothing to do with maths. You mean with labels, huh? Yes. Yeah. That I think you will have to write the code yourself. Yeah, that is not there by default. Yeah. No, because yeah, that's the problem, right? No. For like I can write the command as a loop, but just vertices and edges. No. Yeah, actually you are right. Yeah, because ordering is the problem. Ordering is the only problem. Yeah. Otherwise, it should work. The problem is even if I give 1, 2, 3, 4 and 4, 3, 2, 1, these will be considered as different. Although for us, mathematically, they are the same. Even label wise, they are the same because as sets they are same. So yeah, what I could do is there is a set function, right? Not this. Wait, yeah, this is this only. Yeah. Yes. So I can convert to sets and check. Yeah, you're right. So then I will I'll tell you what to do. I will actually define a new graph, which is actually just K, but with vertices defined in a different order. Okay. So I'll define 3 first. Say it is adjacent to, let's say 2. Then 2 is adjacent to 1. Is adjacent to, yeah, that's it. What did I miss? 1 is adjacent to 4, right? Yeah, that I missed. Okay. Okay. It actually orders it correctly. Why is it? So I think something has changed. Earlier it was not like that. Earlier it would keep the correct, I mean, keep the original order. So even here, not only 3, 2, 4, 1, it will actually say 3, this 2, then 1, then 4. Huh? Yeah, if it's a string, it won't order. But earlier, even with numbers, it used to not order. I think they've changed. They've possibly changed it to reorder it whenever the vertices actually have some order. Yeah, so in that case, you can just check. Oh yeah, see now it is yeah. So it does work. K equal to L does work. Yes. So it will actually tell you graph equality. Yes. Yeah. Yeah. Yes. Yeah. You can, yes, you can convert between lists and arrays. List of, if you give list of function, it will convert arrays to lists. So in fact, to create arrays, you need extra work because array is not a default Python data structure. List is. For arrays, you need something like NumPy arrays or SymPy arrays. So there are array is also one package. So you need to load the package to use arrays in the first place. But yeah, they're basically arrays are built from lists, but they are a different data type. And you can convert back to list easily. Similarly, set is there. You can convert between sets and lists. Yeah, so K equal to L does work. Right. I was expecting that it won't, but it does work. Although it's literally not the same thing in Python. Right. Correct. Okay, so subgraphs also you can define. Okay. So if you give, yeah, I'll actually use K rather than G. Or in fact, H is there, right? It is a big enough graph. I use H. Now let's say I want to get the subgraph of H, defined induced by a particular list of vertices, set of vertices. So let's say 2, 7, 1, 3, and 5. Right. So this, as you can see, it is giving the induced subgraph. Induced subgraph means whatever vertices you have given, it will take that as a vertex set. And whichever edges are present in the original graph between these vertices, those will also be present in the induced subgraph. Right. So maximum possible edges which are there in the original graph, right? Without changing the vertex set. It gives you induced subgraph. Suppose I had made it 4 instead of 5. No, still you don't get a cycle. Okay, let me change it to 1, 2, 7, 4, 3. Right. Yeah, we get some cycle. Yeah, here I've given 10. But again, like the add edge thing, add edge, if you give a vertex which is not there, it'll just add it. Here, what it will do is it will give you the subgraph induced by whatever vertices are present there. So it just ignores the one which is not there. Yeah. I guess you can think of it like set difference. If you do A minus B, difference of sets, and some of the elements of B may not be there in A at all, but that's okay. It's mathematically still defined. But whatever is there, you remove them. Whatever elements of B are there in A, you remove them. Whatever is not there, ignore. So it is doing something similar. Yeah, okay. Now, so this is a bit tedious, manually having to define each graph, and maximum what you can do is add vertices and edges or take complements and so on. But rather than that, I suppose I want to cycle on 10 vertices. I don't want to sit and type all the adjacencies here. So all the standard graphs that you can think of, right? Not the very obscure ones, but many of them which you are familiar with, all of them which you're basically familiar with, many of them which you're not even familiar with also, but which are standard named graphs. These are all already available in Sage. So what are the standard graph families that you can name? Can you tell me? Cycle graph, complete graph, trees, paths. So tree is not a family of graphs, it's a class. Family means you specify the parameters. Then for each complete specification of parameters, you get one graph. If I say cycle on 5 vertices, there is one cycle on 5 vertices. If I say tree on 5 vertices, is that one particular graph? No. That's a class of graphs, right? Tree is defined by a property, right? Bipartite graph is defined by a property. Whereas cycle is defined by the structure is completely specified once I give the number. So path, cycle, complete graph. Yes. Yes. Peterson graph is very specifically one graph. Generalized Peterson graph is a family. Peterson graph is one particular graph. Eulerian graph is a class of graphs because it's defined by a property. Eulerian Hamiltonian graphs are defined by properties. So if I say, give me the Eulerian graph of order 10, there is not one, there are several. Whereas if it's a graph defined by a parameter or one or more parameters, then that is already there. So let's see all of these. Okay, so what do you guess? Yeah, this is maybe not easy to guess. So there is a not capital G graph, but small g graphs. This is a particular object already defined in Sage, which has all the standard graph families. So if you do graphs dot, and let's say cycle graph on 10. Okay. So let's say I will name it as C10. Okay. There it is. Now you can guess the names of the other graphs. Path, complete graph, even complete bipartite graph. Rather than saying bipartite, if I say complete bipartite, that is also a family of graphs, right? But how many parameters? Two parameters. Complete graph is one parameter. Complete graph of order 10, there's one. Complete bipartite graph with two parameters. Order 10 means there are several, right? It could be 1, 9 or 2, 8 and so on. So you have to specify M and N. How many vertices in the first partite set? How many vertices in the second partite set? Okay. So if I say like K34, let's say I'll give K on 3 underscore, then is equal to graphs dot. So what do you guess? Complete bipartite? Complete bipartite. That's it. 3, 4. Here it is. Here I did not specify the layout. But why is it so nicely plotted? Because there is a, yeah, when you take any of the standard graphs, the layout for these graphs is manually defined. Manually means not we are defining, but it is defined very specifically in the library. So there is a way, if you want to plot a graph always in a particular way, I want this vertex in this particular position, this vertex in this particular position, and so on. There is a way to specify that. There is a method called dictionary of positions. So you can additionally specify along with the graph, either while defining it or after defining it, you can give a dictionary of positions which will exactly place it. Just like in ticks, if you are typing in ticks and constructing a graph, how you would specify the vertex position. Similarly, here also it is possible to do it. So that if you use that, then always when the graph is plotted, without any layout being specified for it, it will always show in that particular position, in that particular layout. It will not change it. So for standard graphs in Sage, these are already defined. The nicest, the most familiar positions are already defined. So that is why cycle graph will always come with circular layout. Complete graph will always come with circular layout. Complete bipartite graph will come with this particular layout where you can see the partite sets clearly. First partite set is 0, 1, 2. Second is 3, 4, 5, 6. So another thing you will notice is that if you don't specify the vertex labels, the default labels are 0, 1, 2, etc. What default labels are 0 to n minus 1 if you have n vertices. Okay. So path graph is this. Again, path graph is given this obvious layout. Okay. Then you can, of course, take different graphs from standard families and then modify them according to your needs. Suppose I want here, say, 2 and 4 should be adjacent. So basically, I want graph where it is 0, 1, 2, 3, 4, and then 4 is also adjacent to 2. So instead of defining the graph from scratch, I can just take P5 and then P5 dot add edge to 4. Okay. The thing is, it will modify P5 itself. So maybe I'll not call it P5, which is wrong. Let's say I'll call it H5. So you don't have to start from scratch. That is the point. Can you predict the output? What will it show? Anything wrong? Not modified it, is it? Yeah, layout is the edge is there. You can't see it because it's hidden behind the other two edges. You can see that it's slightly thicker. If you are in the habit of noticing slight problems in right in display of these things, you can see that these two edges are slightly thicker because they are not actually just those two edges, it's three edges. Yes, you watched Monk. So if you change the layout, you can see it clearly. Okay. So when you modify a standard graph, it is not going to change the layout unless you delete some vertices. Right? Then possibly it will change. Okay, yes. So there are some requests about. Okay, sorry, I did not see this earlier. Okay, so in some systems there is a problem with so for plotting, Sage uses matplotlib library. So in some systems, there is a problem with matplotlib library, even though you just installed Sage. There are some issues which will cause the matplotlib library to give an error when you try to plot it. So the kernel will die. Okay, so that has to be fixed separate. There are some fixes, but it's quite difficult. Okay, so I'm sorry, that is the problem. Bipartite graph, as I said, it's a class of graphs. So we will see how to define classes like trees and bipartite graphs also. Star graph and wheel. Okay. So this is the wheel graph of order 10, right? The wheel graph of order 10. So the outer cycle has 9 vertices. Okay. Yes, Peterson graph is also there. It's just one graph, so it doesn't need any parameters. Right. It's a Peterson graph with the most popular layout. There are some other nice layouts also. It's the most popular. Right. What is the other one? Star. So again, star is of course the complete bipartite graph. But again, if you ask for star graph, it will give this layout. Whereas if you say complete bipartite with 1 comma 9 instead of this, you will get this layout. Because the layouts are hard coded. Yeah, the default vertex labels start from 0. So there's a question also in the chat about whether we can get vertex labels as ABC, etc. if you use the standard graphs. As far as I know, no, you can't. You can write loops to relabel them possibly. You can create copies where the vertex labels are some custom labels which you give. But by default, no. As far as I know, it's not possible. It's again hard coded. Like the code that generates these graphs, the functions that generate these graphs, they are set to use 0 to n minus 1. Great. Yes. So we'll now have a tea break for 10 minutes.